In this video, we are going to talk about the image formation in spherical lenses. To determine the image, the location of the image, the orientation, and including the size of the image formed by lenses, we are going to use the ray diagramming technique. Ray diagrams are used to locate the image formed by a lens, and there are three basic rays that can be drawn, but only two are needed to determine the image location. So we have here a diagram showing the image formation using a convex lens. So we have here the object, we have here the object and the image. Okay, so we have three light rays coming from the tip. The first light ray is this one. It refracted, proceeded to the focus, and then proceeded that way. Another ray is drawn from the tip, passes through the optical center, and then another ray coming from the tip passes through the focus and then refracts parallel to our principal axis. There are key rays in ray diagramming. These are the rays that we have to bear in mind as we go through this lesson. Ray 1, a ray parallel to the principal axis, passes through or appears to pass through the principal focus after refraction. So in this case, for convex lens, ray number 1, which is color blue, will refract to the focus. So as long as the ray is parallel to our principal axis, it should refract towards the focus. For concave lens, our light ray will be parallel to our principal axis and will diverge based on our focus here. So it will go that way. For ray number 2, a ray passing through the secondary focus of a converging lens or appearing to pass through the secondary focus of a diverging lens emerges parallel to the principal axis. So in convex lens, if the ray will pass through the focus, it will refract parallel to our principal axis. But for the convex lens, if the ray is directed towards the focus on the other side, it will refract parallel to our principal axis here. For the third ray is a ray passing through the optical center of the lens is not deviated. It will not change its direction, therefore it will not refract. So on the convex lens, as long as the ray 3 or the ray will pass through the optical center, it will proceed as it is in a straight line. For the concave lens, the same will happen. As long as it will pass through the optical center, it will not deviate. In finding the image, any two of the three rays can be drawn to determine the image. The intersection of these rays, the refracted rays, provides the image location. For example, we have here the object. We're going to use the light rays coming from the tip of the object. So the first ray is the parallel ray from the tip directed towards the lens. As discussed, that ray will refract towards the focus. Another ray is coming from the tip. When it passes through the optical center, it will not deviate. So it will go that way. So on the other side, we can see that there is an intersection of the refracted rays. So that intersection, the same with our discussion for the reflection of light, will serve as the point where we can locate the tip of the object. So that's the basis in drawing the image formed by the convex lens. So I repeat, the intersection of the rays provides the location of the image. For convex lens, the type, orientation, and the size of the image depends on the object's location. So if the object is moved farther from the convex lens, the type, orientation, and size of the image will also vary. If we're going to move the object towards or near the convex lens, the resulting image will also vary in terms of the type, orientation, and the size. For a concave lens, the intersection of the rays differ to the intersection of the rays in convex lens. So in this case, we have here the object. A light ray is drawn from the tip parallel to our principal axis, and as discussed, it will refract that way. So the direction of the refraction of the light ray will be based on the straight line from the focus here. Okay. Another light ray from the tip will be drawn, allow it to pass through the optical center. So as discussed, if that is the case, it will proceed in the same direction, in a straight line. Now, there is an intersection between incident ray number 2, the ray passing through the optical center, and the extension of the refracted ray number 1. So here is the intersection. The intersection will provide the basis for us to draw the image. So as you can see, the image formed is virtual, upright, and reduced. So always, the image formed by concave lens will always be virtual, upright, and then reduced. If you're going to ask, what will be the basis in saying that the type of image is virtual? And when can we say that it is real? So for virtual images, the virtual images are formed on the same side as the object. So if this is the object and the image is formed on this side, on this side, the image is virtual. But if the image is formed on the other side, on this side, we have a real image. So I repeat, if the object and the image is or are located on the same side, the image will be virtual. But if the image is formed on the other side, the side opposite to the object, the image is real. So in this slide, we're going to have examples of the image formation by a convex lens. We're going to use the ray diagramming. So our main goal is to locate the image formed by this convex lens. So the setup is the object is placed beyond the focal length of the lens. So this is the focal length. We have the other focal length on the other side. So the first step is to draw a ray from the tip of the arrow or the object that we're trying to uh, analyze should be parallel to our principal axis, and as discussed, it will pass through the focus on the other side. Another ray will be used. You're going to draw another ray from the tip, allow it to pass through the optical center in a straight line. So as you can see, there is an intersection on this part. So that intersection will provide the basis in drawing the image. So as you can see, if we're going to compare the image formed versus the object, the image formed is larger, it is inverted, and since it is formed on the opposite side, at the opposite side versus the object, it is real. So the characteristics of our image, for the type, we have the real, orientation inverted, and then size is enlarged. Another example, the setup is object placed beyond the focal length of the lens. The same with the orientation of our first example, but we just move the object nearer to our lens. So again, the first step is to draw a parallel ray to the principal axis. It will refract toward the focus. And then another ray will be drawn from the tip, allow it to pass through the optical center. Then we can see the intersection here. So that will be our basis in drawing uh, the image. So again, since the image is formed on the opposite side, the type is real, the orientation is inverted, and the size is enlarged. Another setup is we're going to place the object at the focal length of the lens. Again, draw the parallel ray, allow it to pass through the focus. Another ray from the tip, allow it to pass through the optical center. It will proceed in a straight line. Now you can see that the refracted rays are parallel to each other. They will never intersect. If that is the case, no image will be formed on this side. Okay? If we're going to extend the refracted rays backwards, again, since these rays are parallel to each other, no image will be formed even on this side. So therefore, since there is no image formed, there will be no characteristics for the image. If we're going to move the object between the focal length and the optical center, will there be image formed? Let's find out. First, we're going to draw another parallel ray, allow it to pass through the focus, and then another ray from the tip towards the optical center. We can see that there is no intersection between the refracted ray number 1 and number 2. But if we are going to extend the refracted ray backwards and then the other refracted ray backwards, we can see an intersection of the extensions on this part. So that will be the point where the image will be formed. So this is the image and this is the object. So what happened? It is enlarged, it is upright, and since it is formed on the same side with the object, then we have the following characteristics. Type is virtual, it is upright, and then enlarged. It is larger than the actual object. So that's for the convex lens. Now let's proceed to the concave lens. The setup is the object is placed beyond the focus of the lens. So let's start at this point. The first step is to draw a parallel ray from the tip of the arrow, and then it will diverge, as we have discussed already, from the focus here. Okay. So if you're using a graphing paper, all you have to do is to place the ruler from the focus to the point here, and then draw a line from the focus, extend that towards that way, you'll find the refracted ray. Just make sure that the uh, this line should be broken to indicate that it is an imaginary light ray, because this is not an actual ray, an actual light ray. Another ray will be drawn from the tip, allow it to pass through the optical center. So we can see the intersection between this line, these broken lines, and then the second ray. So the intersection will serve as our basis in drawing the image. As we can see, the image form is smaller than the object. This is the image, this is the object. It's upright and then reduced. And since the image is formed on the same side with the object, the type of the image is virtual. Okay. Anyway, if you're curious, uh, how will it look like if you're going to use concave lens? Uh, to your perspective, we'll draw an eye here. So this will serve as your eye. You're going to look that way. You're going to look at the object. The resulting image will be smaller. Okay. Now, what if we're going to place the object at the focus of the lens? So again, first step, since this is a concave lens, we're going to draw a parallel ray. It will diverge from the focus. Okay, and then next ray will be drawn from the tip, allow it to pass through the optical center. We'll find the intersection here. So again, when we move the object towards the lens, still the image is smaller than the object. It is upright, and since it's on the same side of the object, it is virtual. So the image is virtual, upright, and then reduced. So what if we're going to place the object nearer to the lens? So again, same step, draw a parallel ray. It will diverge from the focus. Another ray from the tip, allow it to pass through the optical center. Okay, so we can find the intersection point here. So we're going to draw the image there. Again, the same with the first two examples, the image is still smaller than the object. It is upright and then it is virtual. It justifies it. This will be our proof that for a concave lens, always the image formed will be virtual, upright, and then reduced. So in summary, ray diagrams are essential tool for understanding image formation and in lenses. And there are three basic rays that we're going to utilize: the parallel ray, focal ray, and the optical center ray. The image is located at the intersection of any two rays. Thank you for listening.